Let's take a look at this problem from your homework. We want to use Stokes' theorem to find this line integral where f is x squared y in the I direction, 1/3 x cubed in a j, and xy in a k. C is a curve of intersection of the hyperbolic paraboloid and the cylinder oriented clockwise from above. So if we look at that, if we remember, the hyperbolic paraboloid is like a Pringle type shape saddle. And if we want to look at it from the top, we see the xy plane oriented counterclockwise. So the only relation we want to make out of this is that that the orientation will become positive in a j or in a k direction when we're looking at the surface. Alright, so this is in fact going to be our surface, and this is going to be the boundary of our surface when we change this into a flux integral. So we have a line integral. According to Stokes, this becomes a flux integral over the surface that we were just talking about with this domain, and we want the curl of the vector field dotted with the surface element. Alright, so let's step aside and take the curl, and imagine this x and a y and a z partials over here. So when we look at the first component, I want the derivative of this with respect to y, the derivative of the last term with respect to y. Give us x minus the derivative of the middle term with respect to z. There's no z's in there. The middle term, let's throw a negative sign. The derivative of the last term with respect to x, and then the derivative of the first term with respect to z. Again, there's nothing. And then the last term would be the derivative of this thing with respect to x. That would be 3. That would be just x squared. And then the derivative minus the derivative of the last one, the first one with respect to y, that's x squared, so that goes away, becomes 0. So our curl ends up looking like this. Now the parameterization for our surface, we want to, I guess for now, let's keep it as x and y and then change into polar later on if we have to. It looks like we will have to, since this is the shadow that our surface will make. And so we have x will remain as x, y will remain as y, and z will be y squared minus x squared. And we want to check the orientation. We're going to integrate this with respect to x and y, and take the derivative with respect to x and y. 1, 0, with respect to x is minus 2x, and with respect to y, 0, 1, positive y, 2y. And so when we cross this, we're going to reveal our orientation, and when we cross this, we got the first term, let's see, so it's 0 minus negative 0 minus, and then negative 2x, and then with respect to y, or in the y direction, we got a negative, and then we got a 2y minus 0, and then in the z direction it's just positive 1. So the fact that it's positive means we have the correct orientation. Let's call this OPP, orientation preserving parameterization, and it might be better if we rewrite this a little bit neater. This would be a positive 2x, negative 2y, and a positive 1. Okay, so now let's throw it in here. This is our orientation. This is our parameterization, and wherever we see a z, we're going to replace it with y squared minus x squared. There's no z's in there, and so we just put in these values. So our domain, remember, is this. We have a positive 1 for the orientation preserving parameterization. We got x minus y and 0. We're going to dot that with 2x minus 2y and 1. And then we're going to integrate with respect to x and y. And so let's multiply this out. We have 2 x squared plus 2y squared dA, and remember our d is a unit circle, and so going polar for this, I'm going to change all the x squared plus y squareds into r squareds, and we have change our dA into r, dr, d theta, and there's no other major changes here. So let's integrate this. 2r squared, so that's the integrand. The dA becomes r. dr, r goes from 0 to 1. d theta, theta goes from 0 to 2 pi. So this is r cubed. So that's r to the 4th over 4, and then there's a 2 out there, so that makes it a half from 0 to 1, and then we have 2 pi just sitting out there, the integrand with the theta. So the 1 goes in here, we just get 1/2 times 2 pi. Looks like this is just going to equal a pi. Okay, that's the first part of our problem. We can put this into the computer and see what it says. Let's give that a try. And it looks like our answer is pi. We got the positive orientation going and everything, so let's check our answer. And then, so that looks good. The next thing they want us to do is to graph both the hyperbolic paraboloid and the cylinder, and so we can see the domain. Now these graphs are kind of, they look a lot alike. I guess it would be good to know which one it is, and it would be good for us to graph it as well. So the subtle differences are how big the cylinder is. This looks like it has a cylinder, a radius 0.5, so we don't want that. Same with this, radius 0.5. Our cylinder has radius 1. So now the difference is the orientation of the hyperbolic paraboloid. So what we want to do is we want to check to see what happens when x, this is your x-axis, when x is positive 1 and y, this is your y-axis, y is equal to 0, what would that be? So when x is equal to positive 1, and using this function, when x is equal to positive 1, and y is equal to 0, z is equal to negative 1. And so x is equal to positive 1, y is equal to 0. In this case it's plus, so in this case it's down below. So I think this would be it. This would be the orientation for that. But I think what would be good for us to do is to actually put it in a 3D plotter. And so in a 3D plotter I have this started over here. You can see that the x-axis is over here and the y-axis is this way. So when x is equal to 1 and y is equal to 0, and I would actually see myself down here. So let's see if we can trace this. We have a little dot following there. When x is equal to 1 and y is equal to 0, we're down below here. And we can get our z value over here. Say z is equal to negative 1. It would sometimes be useful for us to take a look at the cylinder as well, but unfortunately the cylinder is not a regular function. So what we need to do is we need to include a special graph. This is an implicit surface graph. We can actually graph a parametric surface out of the cylinder, but let's do an implicit surface instead. So x squared plus, whoops, that's x squared plus y squared is equal to 1. And let's graph that, and we see the cylinder. So the next thing to do is to try to figure out this line or curve of intersection. And so for that, what we need to do is we need to pull out a space curve. And if we look at that curve of intersection, the domain is just a circle if we look at it from the top. So really just a circle. So let's do a sine and a cosine, and then the z is just this z function over here, but remember the y squared comes first. So I'll just say sine t squared minus cosine t squared. And if we just do this from 0 to 2 pi, that should be good enough. And let's hit graph. You can see maybe we can make the surfaces transparent. We can see the curve there, and maybe an even better shot is to get rid of the surfaces. Let's see if we can get rid of the wires for the surfaces. And there goes a curve that we would have had to parameterize had we went directly and tried to do the line integral. And the orientation, according to this, if we look at it from the top, it is going to be, in fact, a counterclockwise direction. See the arrows that were produced there. And so that counterclockwise direction will produce a positive or an upward orientation, which we got correct in our graph. Okay, so I think this is a good parameterization with an appropriate orientation. So if we finish this problem, let's finish this problem. Over here, where it's asking us for the parametric equations. Comma separated, x, y, b in terms of t. Okay, so let's see, x equals cosine t is what we got, y equals sine t, and z is equal to sine t squared minus cosine t squared. And let's see if it'll take. Didn't like our second answer here for some reason. Oops, I'm sorry, I clicked on the wrong one. No, that was the right one. Let's try this answer. Now, this is the right one, so we misclicked it. And I think I chose the upper right hand one instead of this one. Okay, so that completes our look at one of the homework problems.